When we started talking about the material in section 5.1, I said we're actually going to try to make a connection between these areas under curves that we're finding and antiderivatives. And one of the things I remember about derivatives and antiderivatives is that if I start with position and I take its derivative, I get velocity. So one way to think about that is the antiderivative of velocity should give me back position. So I want to talk about an interesting connection between these areas, velocities, and positions or distances. And so there's a video after this that discusses the ideas of displacement rather than distance traveled. But what I have here is some object moving in a straight line, and in this function, v of t is giving me its velocity. And what's really nice here is that the velocity is always positive, so I can just think of it as speed. So, what I want to do is calculate the area under this curve the way we have been. This time though, instead of trying to think about upper sums or lower sums, I'm just going to use the right-hand endpoints. I finished the last video by saying that we might make that choice every once in a while, so I figured why not. One convenient thing here is looking at the way I've drawn this, it also looks like it's an upper sum, but it doesn't have to be. So I'm just going to use the right-hand endpoint. So I need to approximate this area. There's not a lot of information. It doesn't tell me how many rectangles, but I think the most convenient thing to do, just looking at the picture, is to chop up my x-axis every 5 seconds. Right, time is being measured in seconds. I have a point plotted every 5 seconds, and I can imagine drawing those rectangles. And I know what you're thinking. This question, we were talking about distance traveled to start the video. And then I started finding an area, and that seems super weird. Well, let's find the area, and then maybe we'll figure out that there's a connection to distance. So this area I'm looking for, area under the curve v of t, would be approximated by adding all of these rectangle areas together. Well, every single one of these would be a function value times a delta, and I'm calling the independent variable t, so I better call that t. And delta t is 5 seconds, right? Each one of these is 5 seconds long. And so I can look at my rectangle and read off its height and multiply it by 5. So that's 1 unit long, so that's 1 times 5. And then I look at this one, and this one is 1.5 units long, so that's 3 over 2 times 5. Plus, I just need to keep going until the end. So again, 3 over 2 times 5 plus 2 times 5 plus 5 over 2 times 5, and then finally, plus 3 times 5. And I can find that. So I have 1, 2, 3, 4, 5, 6 rectangles, and I should have 1, 2, 3, 4, 5, 6 function values times delta t to get together. And so I need to do that, and so I'll type that into my TI-83 here. And I get 57.5 as that area. But now I want to think about units, right? Because on the x-axis, that distance here, well, that's time in seconds. The height is a velocity in meters per second. So when I multiply those together, I get meters. And what I've secretly been thinking about the whole time is a very old formula that distance is equal to rate times time. Each one of these rectangles is a rate times a time. And so what I'm really secretly doing is I'm pretending that my object was in motion using this rate over the whole interval. Well, if that was true, that rate times time would give me the distance. Well, I'm overestimating the distance because that was the highest rate, not necessarily the rate it traveled. And so each one of these calculations is really a little rate times a time, and so my units end up being meters. And that this area under the curve actually ends up being an approximation for the total distance traveled. Now it's important that in this example I had a velocity function that was bigger than 0. If my object was traveling in that straight line and it turned around, the velocity could be positive or negative, so instead of using velocity for this calculation, I'd have to use speed.